Welcome to The Explainer. Today, we're going on a journey to trace how we went from electricity as this raw, untamed force of nature to the incredibly complex circuits that power, well, everything in our modern world. And it all starts with one big question.
Right. How did we get from a flash of lightning to the smartphone you're probably holding right now? Well, the answer is this incredible engineering quest, a series of problems that had to be solved one by one. It's a story that takes us from just controlling electricity to literally building the brains of our digital world. So let's jump into the very first challenge.
First things first. Before you could build anything with electricity, you had to get a handle on it. It had to become predictable, controllable. You had to make it useful. Okay, the easiest way to wrap your head around this is to think of electricity like water in a pipe. Voltage, that's the pressure, the force that's pushing everything along. Current is the actual flow, how much electricity is moving. And resistance, well, that's like a kink or a narrow spot in the pipe that makes it harder for the flow to get through. So, along comes this German physicist, George Ohm, and he discovers this beautifully simple and totally crucial relationship. It became the bedrock for all circuit analysis. He realized that if you keep the pipe the same size, that's constant resistance, and you crank up the pressure, or voltage, the flow, or current, goes up too. But if you keep the pressure the same, and you narrow the pipe, increase the resistance, the flow goes down. This elegant little insight is what we call Ohm's law. And this core idea defines electrical power. It's not just some abstract concept. It's literally how they calculate your electricity bill and how engineers design the charger for the very device you're watching this on. It is the absolute foundation of everything that comes next. All right, so once we had the basics down, circuits started to get, well, complicated, really complicated. And that led to the next huge challenge for engineers. How do you even begin to analyze these sprawling networks without getting completely lost? I mean, can you imagine trying to figure out the water flow in every single pipe of an entire city's plumbing system all at once? It would be a mathematical nightmare. Engineers desperately needed a shortcut, some way to simplify the whole mess.
So you're an engineer and you're staring at this absolute spider web of components. Trying to analyze it one piece at a time, it's not just incredibly slow, it's a recipe for making a mistake. They really needed a breakthrough.
And the solution that came along was a stroke of absolute genius called Thevenin's theorem. What it lets an engineer do is take that whole tangled, complex network and replace it with something ridiculously simple. Just one voltage source and one single resistor. It's like magic. All of a sudden, these massive problems became totally manageable. Okay, controlling the flow was a huge step, but it wasn't enough. For circuits to do more interesting things, like timing or filtering, they needed a way to store energy. They needed a kind of memory. And that's where the capacitor comes in. The best way to think about it is as a tiny, rechargeable bucket for electrical charge. It can store energy in an electric field and then charge up or discharge almost instantly. This ability to charge up and then stop the flow of direct current once it's full, that's the key. It's exactly what powers the flash on your camera, and it's also used in smoothing circuits to give clean, stable power to pretty much every single electronic device that you own. Now, the capacitor has a partner in crime, the inductor. While capacitors resist changes in voltage, inductors resist changes in current. They're kind of like a heavy flywheel. They store energy in a magnetic field to keep the current flowing nice and smooth, which makes them perfect for filtering out unwanted electrical noise from a power supply. So let's recap. We can control electricity, we can simplify crazy circuits, and we can even store energy. What's next? Well, the next quest was all about taking tiny, weak signals and making them powerful enough to actually do something useful in the real world. How do you take that faint little whisper of an electrical signal from a microphone and boost it so much that it can fill an entire stadium with sound? The answer is a process called amplification. And it was made possible by what is, I think you could argue, the single most important invention of the 20th century, the transistor. Before this little guy, amplification meant using these big, hot, fragile, and power-hungry glass vacuum tubes. The transistor did the same job, but it was solid, tiny, and way more efficient. At its heart, it's just a microscopic electronic valve. Now, here's the really crucial point to get. A transistor doesn't just create energy out of thin air. It's much cleverer than that. It uses a small, delicate input signal to control a valve. That valve then shapes a much, much larger flow of energy coming from a power source, like a battery. It's basically sculpting a powerful current into a perfect, bigger copy of the weak one.
So, with all the key building blocks finally in place, the final stage of the engineer's quest could begin. This was the big one, to make everything smaller, faster, and cheaper, on a scale that was previously unimaginable. This was the dawn of the Silicon Revolution.
And the pace of this revolution is just breathtaking. We went from glass tubes the size of a light bulb to the first handmade transistor in '47. A decade later, the integrated circuit put a few of them on a single chip. And then the pace just exploded. From thousands to millions and now to billions of transistors, all packed onto one tiny piece of silicon.
And the result of all that? A modern microprocessor, the kind that's in your laptop or phone, has well over 1 billion transistors. Each one is a tiny microscopic switch, all working together in perfect concert to perform calculations at speeds that are just mind-boggling.
So, we've gone on this journey from a simple little rule about pressure and flow all the way to circuits with billions of parts that can fit on your fingertip. This engineer's quest has completely reshaped our planet, and you have to know it is far, far from over. The real question is, what problem will it solve next?